Okay, hello. So this is chapter 8 for flood routing. So hi, good morning, good evening, or good night, depend on your time you're watching this. Uh, so this is part 3 for channel routing. Okay, so for part 3, it's hydrologic channel routing. So I hope you still remember what's the difference between channel routing and reservoir routing. So remember channel routing, it's the same with its name, channel. So there is no reservoir, it's just channel. Okay, if you remember in the previous slides, I think it's in part 1 where I showed you some difference between reservoir routing and channel routing. So one of it is how we determine the flow of the outflow. So here it says here in reservoir routing, the storage is a unique function of the outflow discharge. Okay. So it depends on the outflow. It depends on this outflow information. So if you remember reservoir routing, you have inflow and then you have the storage information, and then from that storage information, you can get the outflow. Okay, by the relationship of the outflow. Okay, remember the storage outflow relationship. So that is for reservoir routing. But for channel routing, okay, the storage is a function of both outflow and inflow discharge. Okay, so information for the storage, uh, inflow and outflow data are used to determine the storage. Okay, for reservoir, yes, there is also inflow being used, but the formula, not the formula, the mechanism where you calculate, it depends on the outflow. Okay, the hydraulic structure information. Okay, but for channel routing, there will be some formula where both inflow and outflow is used in the equation. You will realize it later, the difference. Okay, and the other information here, flow in a river during a flood. It belongs to the category of gradually varied unsteady flow. Okay, so this is in hydraulic. I'm not if you already took the hydraulic class, then you will realize there is this information on gradually varied unsteady flow. So gradually varied unsteady flow, it depends on two things, which is changes in the cross section. No, changes in the yes, of course, cross section, but also the changes in the flow. Okay, from along the river or open channel. And then there's one more information, changes in the flow according to time. So there are two, according to time and according to cross section, or in this case maybe the water level, yeah, or the flow. Okay, so that is what means by gradually varied unsteady flow. Okay, and the water surface in a channel is not flat. Okay, so this means that the water level changes. Okay, so this is just the concept of hydrologic channel routing. Okay, so remember it's a channel or open channel, so it should look like this. This is, if you would say open channel, it will always be drawn like this if you realized it. So it is not only parallel to the channel bottom, but also varies with the time. Okay, channel bottom is here. Okay, you may see it as parallel, but okay, but there is some additional like a storage here. Okay, no, okay, this is the additional storage, the wedge storage. Okay, and the prism storage. So prism storage, if there is no additional flow coming in, like because we are looking at flood routing, so this is what we call it. During flood flow, the channel which can be considered under two categories as prism storage and wedge storage. So wedge storage is the additional flow coming into the channel. Okay, but prism storage, if there is just a base flow, there are no flood coming. Okay, there are no additional rainfall coming in, so that is what prism here means. So it's parallel to the slope. Okay, but when there is some rainfall and then there will be some hydrograph form. Okay, hydrograph formed, there will be some peak discharge, and you know this shape. Okay, because of this shape. Okay, if there are no rain, the river will be just like flat. Okay, but because of there is some rain coming in and flood coming in, so the hydrograph would look like this. So this prism storage is actually the additional inflow going into the channel. So prism storage is the volume that would exist if uniform flow occurred. Okay, uniform flow, it means that the water level did not change. Okay, but in this case, it changed uh, it changed according to time. Okay, so and that way there is another wedge storage formed between the actual water surface profile and the top surface of the prism storage. So this is just the concept. Okay, so here is more explanation on the wedge storage. So remember, wedge storage is the additional volume of water going in the channel. Okay, so it is called wedge storage. So if you look like this way, okay, this is like a not y-axis. According to chainage, we can say that this is according to chainage, according to some distances. So we have an inflow and we have an outflow. Okay, so if the inflow is higher than the outflow, so the change of the water level according to x. So this is x. Okay, we can say this is x and vertical is y. So the change of the water level according to x. So x is some distance. Yes, some distance. So we can say that dy over dx is negative. Okay, this is for the first case. Why is it negative? Because if you put this is y1. Sorry, this is y2. Okay, and then this is y1. Okay. Advancing flood flow. Okay, I inflow here is larger than outflow. Okay, so y2 minus y1. Okay, so dy over dx is y2 minus y1. Okay, so according to the difference in the location here, so x divided by x2 minus x1. Okay, so we can say this is 0.2, this is 0.1. Okay, we can say it that way. So if the inflow here at 0.1 is larger than outflow, which is at 0.2, so dy over dx will be negative because y2 minus y1 will be negative. Yeah? Because y1 is larger, so it will be negative. And then different case would be if inflow is less than outflow, so you will get a positive dy over dx. And if it's a steady flow, means that there are no changes in the water level. Okay, the water level here is y, so there is no changes in water level, so we can say I is equals to 0. Okay, so this means that the prism storage, the storage is a function of 0. So I hope you understand what does it mean by a function of. Ia berkait kepada, di sini maksud dia storage berkait bersandarkan outflow. Okay, so that is what it means by a function of. So this is the difference, the formula difference between reservoir routing and channel routing. So before reservoir routing, there is they use the continuity equation. Okay, we use the continuity equation, but for channel routing, it's a different case. It's more like a regression analysis, like multiple regression analysis or just a regression analysis. Regression analysis is like the simplest is y equals to mx plus c. So this is actually quite similar to y equals to mx plus c. So the total storage in the channel ridge can be expressed as this way. Okay, so where k and x are coefficients. K and x are coefficients. So this is coefficient. And m is a constant exponent. So it has been found that value of m varies from 0.6 for rectangular channels to a value of about 1 for natural channels. So we can actually find m. So it is just a constant which we can find. So k and x also is a constant that we can find. Okay, S is storage, I is inflow, and Q is outflow. Okay, so if you use m is equals to 1, so it becomes a linear relationship. Okay, so this is linear relationship is like y equals to mx plus c. So if you make a m is a 1, okay, so s will be kx plus 1 minus x q. Okay, and this relationship is known as Muskingum equation. Okay, in this, the parameter x is known as weighting factor. So this x is a weighting factor. Okay, so weighting factor ni in Malay it's apa namanya pemberat, pemberat. So kalau it takes a value between 0 and 0.5. So if it's 0, okay, if it's 0, it will reduce this equation. So we will see it in the next slide. And if it's 0.5, it means that 0.5 ni half kan, half of 1. So it is, we can say that I and Q has the same influence to determine S, because we divide the weightage 0.5, half. Okay, so here when we say x is equals to 0, so look back at the previous slide, the formula. So if it's equals to 0, then we will diminish the influence of inflow. Okay, so here we find it is only s equals to kq. So we can say this is called as a linear storage. Okay, because we are talking about channel, maybe it's more understand if we just know it as a linear storage. Okay. So when x is equals to 0.5, so we can say both inflow and outflow are equally important. Okay, so look back at the formula. If we put 0.5, so both I and Q have 0.5I plus 0.5Q. So it means that both have equal importance. Okay, and K, it is the storage time constant and has the dimension of time. It is approximately equal to the time of travel of a flat wave through the ridge channel. So I may draw like this. If we have this channel, okay, and we have 2 points, 1 and 2. Okay, so for channel routing, what we are doing is we are establishing the relationship between storage, inflow and outflow. So we are establishing the relationship or the formula. So that is what we call the Muskingum formula. Okay, so it has inflow and it has outflow variables, and it has this x, k and m. Okay, so for k, it is the time of travel of flat wave through the channel ridge. So if there is this hydrograph here, and once it reaches at point 2 this hydrograph, so what is the time? Okay, so by definition, that is what k means. What is the time? Okay, what is the time from it travels from point 1 to point 2. Okay, so this is a typical inflow and outflow hydrograph. So it's the same for same thing that I explained before in reservoir routing. So similar to channel routing. So we have inflow and outflow. The blue color is inflow, red is outflow. So if you plot, it will probably look like this. Okay, so we can also use the same like continuity equation, because it is still routing. Okay, so there will be inflow and outflow. In this case, it uses Q. There will be some different in time. Okay, so from this we can get the difference in storage, DS, the difference in storage. So the increment in storage at any time t, it can be calculated. We can estimate what difference in time that we want to use. Okay, and a summation of the various incremental storage values enable one to find the channel storage versus time relationship. So we can look this in the next slide. Okay, so for channel routing, we may also look like this in this way. I minus 0. So we have accumulation of storage and we have release from storage. Okay, and then we can estimate the accumulated storage by just accumulating this I minus O. Just accumulate each value according to the time. Okay, we can just add one by one, so we can get this kind of accumulated storage graph. Okay, here is a little tricky. Okay, a little new concept that is exposed to you. I know this is a new concept exposed to you. Okay, so here we can see. Okay, so this one is what we call the Muskingum formula. Okay, there is a relationship. We want to establish a relationship between inflow and outflow. I and O. We want to establish the relationship between I and O. Okay, using there's this sum factor X. Okay, so X, remember, is the weightage. So we can determine this weightage, okay, by trial and error. So we need to do some trial and error like this. Okay, trial 1, trial 1, trial 2, and then once we get the shape of the graph, it fits as a linear line. Okay, then we can say, okay, so this X is the correct value of X, right, that is suitable for our channel. So this X value, so it depends on channel. Okay, depends on point 1 until point 2 in a certain channel. So it may change depending on the location. So here's some explanation. If an inflow and outflow hydrograph set is available for a given reach, okay. If an inflow and outflow hydrograph set, okay. So first we want to establish this formula, okay, this Muskingum formula. So first we have to have a data of inflow and outflow. Okay, different from a reservoir, we just need inflow information and the hydraulic structure. Remember, the reservoir routing, we only need inflow data and we only need the information of the outflow structure. Okay, remember, but this is channel routing. So for channel routing, we have to have the inflow and outflow hydrograph. Yeah? There is no formula to estimate outflow. It's just directly we use this formula. Okay, there is a formula which directly relates I and O, okay, by this X. Okay, so values of S at various time intervals can be determined by the above technique, okay, by choosing a trial value of X. Trial value of X, so this is X1, okay, this is X2, so we do trial and error, okay, and X3, okay. But we must understand X should be in the range of 0 until 0.5, okay, because it's a weightage. It's a weightage. It's a fraction or weightage between inflow and outflow. So the value should be in between 0 to 0.5. Okay, so if the value of S is chosen correctly, a straight line relationship. So here, a straight line relationship will be developed. Okay, once a straight line is developed using a certain value of X, then we can say, okay, this X is correct. Okay, so we can say we found the X value for this reach, for this condition. Okay, and there is also some tips here. Normally for natural channels, the value of x lies between 0 to 0.3, okay, for a given reach. Reach ni maksud dia stretch of point 1 to point 2 in an open channel. So that is what we mean by reach. Okay, so x and k for this case, for this reach, for this particular channel from point A to point B, so it is a constant. Okay, it cannot be applied to other river. So it is specifically for a certain river and a certain stretch of length in the river. Okay, so other way we may understand this is the values of x. Okay, so it may depends of the condition. Okay, so if there is no wedge storage, means that there are no additional inflow. Okay, there is no additional inflow coming in. So we can say I and O is the same. So that is when we say O, x is 0. But if x is equal to 0.5, then there is some storage full, okay, of the wedge storage full. Okay, so there is some more information here is that we can determine C1, C2, and C3 by known of x, k, and the difference in time. So what is C1, C2, and C3? Okay, so we proceed with some more information for your knowledge. So if we say storage S1, so it refers to condition before, and if we say S2, so it refers to condition after. Okay, so in this case, this is similar to the Muskingum formula. Okay, realize S equals to K X, okay, Xi plus 1 minus X O. Okay, so this is equals to S, the formula that I've shown you before, K, okay, X, Xi, Xi plus 1 minus X, okay, 1 minus X, O, okay. But in this case, because it's a very two times, so we have condition before and condition of after. So this is like the continuity equation. So remember the continuity equation here. So if we rearrange the equations where O2 is evaluated, we want to find O2. Okay, so we can get some kind of constants here. So this is the constants. Okay. So K, so Kx and difference in time, we simplify it. We simplify it in terms of C. Okay, this is C. So you will know why we use this. It's for the steps of the calculation later. Okay, so we just proceed to example. So there's no other better way than just look at example. So for this example, using Muskingum routing, so it's just the same. It's the same as channel routing. Route the following hydrograph through a river. Okay, for which it already gives you K 12 hour and X 0.2. Okay, for this example, they just give you directly what is K, what is X. So at the start of the inflow flood, the outflow is 10. Start of the inflow flood, the outflow is 10. So actually 10, this is like a base flow. Okay, this is like a base flow like this. Okay, there's some base flow. Okay, so hydrograph would be like this. So there is a base flow. So here 10 is like a base flow. So we have K, we have X. K is 12 hour, X is 0.2. Okay, so here are some here, wait, I will highlight this. Here are some tips or guide or what is DT that should be used. Okay, so here we can put like 2 multiplied by K multiplied by X, we have 4.8 hour. So we can say the difference in time should be in between K and this 4.8 hour. Okay, so in this case we just use the dt is equals to 6 hour. Okay, this is because the interval of time Okay, for the inflow hydrograph is 6 hours, so it's already suitable for this case. For this case, so what we do is just count C1, C2, and C3 using the formula. Okay, just use this formula. I think I'm not sure whether this formula will be given or not in exam. Okay, but I'm not sure. I will check later. But just use this formula to get C1, C2, and C3. Why do we need these C values? Because this is the continuity formula. How do we get the outflow? Is just this simplify the formula of the Muskingum formula. It simplifies the Muskingum formula. Okay, so for the first interval 0 to 6 hour, so we know I1 is 10. Okay, for the first I2 is 20. Okay, so O1 is 10. Okay, so just use the formula, just use this formula. Okay. O2 is equals to C1 I1 plus C2 I2 plus C3 O1. Okay, so we get the outflow. 2 is this. Okay, for the next time step 6 to 12 hour, O1 becomes 10.48. Okay. This O1 becomes 10.48. So that is the continuity. The procedure is repeated for the entire duration of the inflow hydrograph. Okay, the computations are done in a tabular form. So if you have Excel, this would be definitely will ease your calculation. Okay, so you can check with this table, okay, using the previous formula, okay, of I1, I2, O1. Okay, so please check the formula and check with this table. Okay, after applying the constants C1, C2, C3, so remember the constants we got from the value of K and M. Okay, K and M. So this example, it is already given. K and M is already given. So we just apply the value of K and M and put it into the formula of C1, C2, and C3, and then use the continuity formula before, and we can get the outflow for each time step. So in the end, we can plot inflow and outflow. Okay, so here is another example. Okay, the example before is we assume that we already got, we already have the K and X. Not assume, the question already give you the value of K and X. So what if we don't have that value of K and X? Okay, so this is when we do the trial and error of which X is the most suitable. So whatever it is, we want to establish the relationship between the storage, inflow, and outflow. So for you to get the formula for, not formula, the value, the constant value of K and X, so the first thing is you need to have some observation data. Okay, you need to have this first observation data just to establish the X and K value. After you have established this X and K value, so whatever inflow data that you get, okay, you can determine the outflow. Okay, so for this, this is just the observation that we have obtained. Okay, but if we have another set of inflow data, then we can use this K and X value that we obtain from this. Yeah. So I will show you in the next step. Okay, so this is the same table. Okay, so we have time, we have I inflow, we have O outflow. So the next step will be you add these two more row. Okay, so this is the first one. This is inflow minus outflow. So you get this for each time step. Okay, until the end. Okay, and then you calculate the storage. So how do you calculate this storage? Is you can use this formula. Okay, so it is like for the first is there would be nothing. So this would be nothing. So the next column would be 0. Okay, plus 14 and divide by 2. So it's the average. This is the average of these two. Okay, and then you need to multiply by
the time, 12 hour. Okay, so why 12 hour? Because this time, the difference in time here is 12 hour. Okay, so don't make a mistake here. So if your time is this different is time is 6 hours, so you need to multiply by 6. But this for this case it's 12 hour. Okay, so you need to multiply by 12. So that is how you calculate your storage. Okay, and then do it for the next time. Okay, so this is just an example of the previous calculation. Okay, it's the same with the table. So you can see here that there are positive and negative values here. So if you look back in the previous slides, you can see this type of graph. Try and find this graph. Okay, so here it says I minus O here. Okay, and x-axis is time. Okay, so this is similar. Okay, but in this case this is as a storage only. So I minus O, or it is storage. Yeah, for the y-axis it is either I minus O or storage. Okay, if you plot this kind of graph, you will make this kind of line. Okay, so here there is positive, okay, and negative. So positive means accumulated or accumulation of storage. And there are additional volume coming in. And negative means the storage reducing, or the volume is reducing. Okay, so that is why you have positive and negative. Okay, then after you get these two additional um, row, which is I minus O, and then you calculate the storage. Okay, so this would be, there will be some positive values and negative values. Okay, so the next step is you do the the cumulation of this storage. Just add it. First there is no, okay, just follow the storage. Okay, so first there are no value, and then 84, and then you just add 84 plus 498, you get 582. Okay, and then 582 you add with 738, so you get 1320, and so on. Okay, so this you can calculate yourself, and there are also example in the next slide. So here, example of the calculation. This is also we also say this as big S, but it is cumulative storage. Okay, this is cumulative storage. Okay, so for this cumulative storage, you will get all positive numbers. There are no negative numbers. Okay. But the thing is, if you want to know if it's correct or not, if you plot this cumulative storage, you will get this kind of shape. Yeah, you will not get this kind of shape anymore. Okay, this is wrong. Okay, for cumulative storage, you will get this kind of shape. Okay, there are no negative values, so these are all the like the hydrograph. It is like the hydrograph. So for the next step, so this is where we start on how do we get the right value of x. So this is when we do the trial and error. Okay, so this is the trial and error. Forget this. So you need to do the trial and error. So you need to have this kind of table. So you have time. Okay, you have inflow, outflow. So this time is still the same. It's the same table before. Okay, 12-hour difference in time, and you need to add this row. Okay, remember this formula. This is like the Muskingum formula. Okay, where x is, you need to find x. Okay, so x, we are doing trial and error. So for the first trial, we assume x is 0.2 here. Okay, so xi plus 1 minus x, this is 1. Okay, this is I. and then multiply by O, outflow. Okay, and then you have this storage, and then you have this cumulative storage row. Okay, these two you have calculated before. You created this, okay, using the equations that I showed you in the last two slides before, in the last previous slides before this slide. Okay, so remember this figure. Okay, this is for the trial and error. You should have multiple graph like this. Okay, so before we assume x1 is 0.2. Okay, the previous slide. So x is 0.2. Then you need to plot x this Muskingum formula. Okay, plot this y-axis using this formula and against the S against the cumulative storage. Okay, and then you need to estimate the next x. Okay, because this one is not closed, it is an open loop. You need to get this kind of graph, then you can say your x is correct. Okay, so this one, if you plot, let's say 0.2, use the x 0.2 and see whether it is a closed loop or not. If it's not, then you have to make another trial. Okay, for the first trial, let's say when we plot okay, when we plot y, okay, this is y-axis, this is x-axis. Okay, let's say for the first trial, before we plot for x equals to 0.2, we didn't get a closed loop. We didn't get, we either get this kind or we get like this kind. So this is wrong. I mean, this is not right. Okay, this is wrong. Okay, so we need to do another trial. So let's say we are doing the next trial. Okay, so I put here x2. So this is the next trial, the second trial. We put 0.25. It doesn't matter, it can be 0.21, 0.22, 0.23, 0.3, 0.3.5. It can be those values as long as the x is in the range of 0 until 0.5. Okay, because this is a weightage. This is a weightage between I and O. Okay, so let's say the next trial we are using x equals 0.25. So you need to put in this x value here. Okay, so 0.25 multiplied by inflow plus 1 minus 0.25 multiplied by outflow. So you get here. Okay, so the next column, x 0.25 multiplied by this inflow plus 1 minus 0.25 multiplied by outflow. So you get here. Okay, and then do for all time step. Okay, this is similar to the previous trial. And so, and then we plot y. Okay, we plot this and we plot this. This is y-axis and x-axis, and then you see again whether you look back whether you get this kind of graph or you get uh, something that looks like a straight line. Okay, so this would be your assignment actually. Okay, whatever is not written here is your assignment. So from the previous x also, x equals to 0.2. So this will be all of your assignment. Okay, and then when we do x equals to 0.25, and then you see whether you get what kind of graph. So you plot the graph. You plot the graph with the you can do this way. Okay, the plot the graph like, oh, this is y, this is x. I taught you before is this is y, this is x. But if you make a different axis, you change the axis, it's okay. But you need to make sure that how do you get the k later. Okay, slope of line. How do you get this k value? So remember, if you okay, this is the condition if you get okay this kind of graph. Okay, so you can get this kind of graph. So you say okay, your x is correct. Okay, because it's try and error. Let's say x, I don't know, x2 is correct. So you need to create your line. You need to create a straight line. Create a straight line here. Identify some point. Okay, and then you calculate the slope. The slope. Calculate the slope of the line. Okay, and then you can get the k value. Okay, or if you plot s storage as y-axis and this is as x-axis, and then you get directly the k as the slope of line. So be aware of this. How do you get the k value? Okay, so we finish part 3. So the last example would be your assignment. Okay, so the last example is your assignment. Do it in Excel. The same way. Just do it in Excel and make sure the cell have the formula. Okay, so thank you. So we can see you in our online meeting. Okay, and then that time just ask me anything. Okay, that's the time where you ask. So you need to make sure you watch this video. Okay, you watch this. That's why you are in the end of this slideshow, right? Okay, so see you tomorrow.